You got some good results?
Mm-hmm.
If you did, awesome. If you didn't, that's even more awesome, because then we have an opportunity to improve things. So please let us know if you found something that was off. It is very difficult to make a system that works well globally. There's so many edge cases. We try to generalize our solutions and make them robust so that they work everywhere. But you can't avoid completely that you find some. So if you did find something, let us know. Otherwise, glad to hear that that things worked. Okay, so a little bit more of a deep dive into the data that underlies this and how we use that to parameterize the model and eventually get to all the output. So a whole bunch of data layers that go in. As I mentioned before, we tend to think of them in these categories around topography, which is one of the major data sets that influences the quality of the final spatial aspect of the flood maps. And then the climatic and the soil components really in nature heavily influence the hydrological response, so the magnitude and the amount of flood water that's eventually going to be available to the hydraulic aspect of the model. Yeah, I mentioned this already. So mostly there's a whole collection sort of global data set that ends up going into this. Just to highlight a couple maybe that are interesting to talk about. For elevation, we do Copernicus 30 as the background layer with our own filter on top to remove buildings and vegetation. And then we merge in the LiDAR data for 25 countries where we have it available in a seamless way. There's a whole bunch of optical imagery like Landsat and Sentinel that we don't always do the own processing. Sometimes we use derived products directly, or sometimes we do our own processing on them. But for things like canopy height and density and land cover classification to estimate surface roughness parameters. Combined land use and soil grids data, which is a global soil physical parameter database. We use that to get the soil physical parameters and estimate those, which is an important input for the infiltration modeling. For rivers, we developed our own global river database combining satellite and national data sets, as well as OpenStreetMap for some of the more detailed urban streams. Urban data is anyway always an issue in this, combining global scale with sort of this level of detail that we're looking for. It's very difficult to find consistent databases for larger areas of things like urban stream flow, flow lines, as well as stormwater drainage systems and their capacities and things like culverts. So we work also with OpenStreetMap data to sort of give suggestions to the parameterization system of where to route things through urban areas. Then on the boundary condition side, we use a lot of reanalysis and satellite-derived soil moisture and precipitation data for the historic aspect of that, as well as the extreme. And like I mentioned, and I'll get into that a bit more, we combine it with station data for improvements in accuracy to eventually get to those boundary conditions. And then for storm and surge level, there's also reanalysis modeling results at a global scale calibrated on observational data that we can draw from there to do that. We also made our own set of snow melt design events, so specific scenarios for quantities of snow melt for various durations that are site specific but available globally, where snow melt is a relevant factor that we can use also for our return period flood maps as an input to the hydrological modeling. Just to highlight a little bit how key some of that data can be. Not sure if I can understand what it. These two models are done with just a standard industry standard Saint-Venant equation solver, shallow water equations on the landscape. Same rainfall inputs, same resolution, both running at 10-meter grid cell size, spacing between the individual pixels in the model domain. But the data here is LiDAR data on the left, and on the right it's a previous generation global satellite-based elevation model, SRTM, the Shuttle Radar Topography Mission. Now this is a bit outdated by now, right? This SRTM used to be the best up until 2020-ish when Copernicus 30 came out. But I do hope it sort of visualizes a little bit the impact that the data quality can make on flood mapping in particular. Copernicus 30 is miles better. It really is, but it's also not. It's more closer to SRTM than it is to to lidar data. Now we merged Copernicus 30. We're available with this lidar data. This shows the countries where we have those available at higher resolutions, and they're used just out of the box for the user. And then we do some filtering on areas where relevant as well to get out buildings and vegetation. There's that's become pretty standard to filter out and use DTMs, terrain models, instead of surface models for flood modeling input. There are resolutions where you could argue that it might be useful to incorporate the buildings, although we follow sort of the typical suggested workflow where we increase the flow resistance for the areas where the buildings are to still incorporate some of the friction that the buildings provide to the flow. To highlight a little bit, Copernicus 30 was really a lot better. You see here a bit of a comparison between that and the previous global satellite product that was available. It really had a strong reduction in noise. This was originally a 7.5 meter product, Tandem X, by DLR, the German Space Agency, and Airbus. I think was a collaboration, and the European Commission licensed this to make a 30-meter freely available model out of that. For surface stuff, right, we lean heavily on visual imagery. Think Landsat, Sentinel 1 and 2 for classification of land cover types, and then we link the friction of the surface to those land cover types. So that's also then available at 10-meter resolution, which is the resolution of the satellite Sentinel visual bands. There's more bands in there that some of those are also used, but the highest resolution bands in there, including red, green, blue, and near infrared, is 10 meters. Soil grids we use heavily for some of the soil data. It's a statistical model for physical soil parameters globally. They combine some machine learning methods with a global set of training data and landscape covariates as inputs. They do predictions of the particular variables, things like soil clay content, gravel, organic matter, silt, things like that, even mineral types. And they also provide uncertainty ranges around that. There's over 100,000 soil profiles globally that go into this. It's a 200-meter gridded product, which is somewhat low resolution, but it's a very valuable resource. If there is local data, it is significantly useful still to use that. But at the scale at which we're doing things, we have been quite happy with providing this as a default option to users, and then they can always load in their own data if they are inclined to do that. And as I mentioned, for river data, we developed our own for two reasons. One is that we need this also to provide detailed boundary conditions in an automated way for our users. And existing datasets either didn't have the detail level or the attributes to do this effectively. So we built one with river splits with the right attributes consistently throughout that takes into account larger rivers, but also smaller streams in one consistent database so that we can use those for boundary condition placement. For larger rivers, we also use it to automatically take out bridges and other larger obstacles that might have still been left in the elevation data. It's not so much an issue with lidar data typically, though sometimes it is. But for Copernicus 30, you do see that bridges become large obstacles that start generating fictitious reservoirs in the landscape all of a sudden. So then, based on this global river data, we filter those out. Getting back to this point about station data, there's this collection where we combine some national and some global collections of hourly precipitation data, as well as daily discharge data. And then we use, of course, as an input for our model, a set of IDF curves for precipitation, for extreme precipitation rates. This is not completed too. The IDF curves also have a spatial dimension to them. So they're intensity, duration, area frequency curves. They're four-dimensional analysis results. But we do an AI bias correction on these stations to improve the accuracy of the gridded ones we originally derived from ERA5 land and GPM IMERC. And we do a similar thing for the discharge data, where we start with the GLOFOS reanalysis data, and then do an AI bias correction on the extreme or the return period analysis that we do on the station data there. This is what the results for that look like. What you see here is the 0.05 degree gridded 10-year return period precipitation intensity. You see on the bottom left sort of the spatial patterns there, which is pretty typical, higher intensities around the tropics especially. But then what's perhaps more interesting, on the bottom right, you see on the left the scatter plot between observed and the gridded data before the AI bias correction, an R value of 0.6. And then on the right, you see after the bias correction procedure, where we increase the R value to 0.864. And again, that's comparing the IDF curves from the observational, the hourly precipitation station data, with the gridded versions derived from ERA5 land and GPM IMERC. So we do see that bias correction procedure really helps significantly in improving the accuracy of these kinds of inputs to the modeling. And a similar thing when we look at the quality of our discharge boundary conditions. If we compare there with the 9,000 or so stations with daily data that have sufficient years to be considered here, we get initially an R squared of 0.85, and then after the bias correction, we slightly increase that, although the other metric shown above it has a more significant increase. But then eventually we do a final secondary step here, where we enforce the observed values within the gridded data sets directly. This enforcement is a bit cheating if you're talking about the predictive quality of the AI model. But on the other hand, we don't really care about the predictive quality of the AI model. All we care about is the end accuracy of the discharge boundary conditions that we use. There is a bit of an overestimation seemingly on the bottom side. That's on purpose. In fact, what we saw in the trends there is that for small streams, there tends to be a significant underestimation of extreme flows. So for flash flood events, those are much more rarely captured, with fewer stations that provide accurate estimates during larger events. So we picked some hand-selected stations where we knew the coverage was longer and good enough. We used those to sort of brute force an adjustment for those lower drainage area regions. And that eventually got the R squared value up to 0.94 between the station data and the gridded estimates there. You see also a little bit how the error is distributed between small, medium, and large size basins. And there you see sort of the same thing, right? The spread is much larger for these small basins. And then based on those hand-picked criteria, we see them move up quite significantly. But that's on purpose in the end. Maybe to show for urban areas, we try to do a lot of estimation of features based on OpenStreetMaps as well. You see here, for example, in red, locations of automatically derived culverts. Then the black lines, the automatically derived bridge locations. And then in the gray lines, the stormwater drainage network, which is assumed to match up one-to-one with the road network, at least for the inlets of that stormwater drainage system. And similarly, those urban areas can be, or urban elements can be used for exposure analysis, for example, looking at impact of buildings within a region. Oh, can I have your charger? For climate change, we do some particularly detailed incorporation of climate change into this. There's a whole bunch of global precipitation sources that you can draw from. And like I said, for our extreme scenarios, our hazard mapping, we draw heavily on ERA5 land and GPM IMERC for a combination of long historical records, which works well for the types of extreme statistics that we want to do, and GPM IMERC for their ocean coverage as well as their spatial resolution. Now, for climate change, things are a bit different, right? We have to look at global climate models, or local, but we use the global ones that move into the future. So what we do is we apply also here our full extreme value analysis, and that's a little bit different from what you see in other studies sometimes, where people look at single metrics like P99, so the 99th quantile precipitation, and how that changes throughout the years in these models. We feel that's a little bit of a shallow look at the effects of climate change on extreme precipitation. I'll show you in a bit what the some of the main outputs are that are different. But for us, the result of this extreme value analysis that we do for these future time windows gives us a way to do a full transformation of the current relation between precipitation intensity and its probabilities to those under climate change. We can also apply that to rescale current disasters that happen and say, what would that same disaster have looked like under a certain climate scenario, under a certain time period. Now we look at the whole ensemble so that we can also give some uncertainty ranges to those climate analysis outcomes, and look at various durations of precipitations, extremes, 1, 3, 7, and 14 day, return periods between 2 and 100 years, and various SSP scenarios that we look at. This method is sometimes called segmented window analysis. We did 4 windows in the end between 2000 and 2100 to cover sort of the range and the changes and the transformations between the extreme precipitation that happen under climate change. Now, this is one of the sort of the main outputs. What you see here is globally a visualization of within that ensemble of global models. What is the 1 day extreme precipitation at 10-year return period under climate scenario SSP 245 and target year 2080? Now, there's a couple things to note here. Even for the single output, I already had to specify 5 different specifics about this map. It's 1 day, 10-year return period, SSP 245, target year 2080, and a certain spatial size is there as well. We try to hide as much of the details about the technical side of this for the user, although they can still dive into that and select that. Our aim was to sort of keep it digestible. What you see here, though, is then for those 1 day extreme events, what kind of relative change are we seeing in the climate models for extreme events? So here, a blue value means that in the year 2080, you might get 30–40% more precipitation for a flash flood trigger than you would get now. A red value might mean you get 30–40% less precipitation during an extreme event. And you see those patterns differ quite significantly globally. There's areas like Sri Lanka, areas like Myanmar, areas like Alaska, where you see a quite significant increase in extreme precipitation. But there's also vast areas like Arizona, like South Africa, like the south side of Iran, where there's very significant, or Morocco, where there's very significant decreases in extreme precipitation. Now, this doesn't necessarily link directly with the yearly water balance. So it doesn't mean that it's going to be drier for those areas or wetter for those areas. It's just the extreme precipitation. So those rare events, those are seeing this change within those models. Now, since we do a full general extreme value analysis also on different durations of events, we can use particular quantities that link to the return periods that the user is doing, to the particular type of flood trigger that they are using. And we see that those patterns are also significantly different, which is something you would not capture with using a single quantity like the P99. On the right here, for example, at the top, you see the one-day analysis. So this is a one-day extreme precipitation event and what kind of relative change that has going into the future. At the bottom, you see the 7-day duration. And while there's areas where it's similar, like Morocco, right, you see a significant decrease for both 1 day and 7 day. There's also areas where there's a much more significant difference between those two. Take, for example, the south of Pakistan, where in the 1 day duration, there's a significant increase of about 10 to 15%, which is saying flash floods might see 10 to 15% higher intensity. And on the bottom, 7 day duration, the longer extreme precipitation is seeing a 10 to 15% decrease. So that's saying fluvial flood triggers might decrease, while flash flood triggers might increase. And there's a couple areas like that where we see reverse trends between or at least significantly different trends between shorter and longer duration, or between 5-year return period extremes and 100-year return period extremes. But that's all captured then automatically in the end by the user. Now within FastFlood, you can select to visualize this any area in the map and say, I want to view some of these data sets, and then select climate trends, for example, to get for that particular site the outputs of this analysis procedure that we carried out, including the uncertainty ranges around that. And these results differ from location to location. Right? They're going to be significantly different for some areas as opposed to others, like you see in the maps that I showed you. There's a very consistent increase in areas like Sri Lanka, but in other areas you might see very different trends altogether. Well, like a significant decrease expected on median for Morocco. Now, this is something that there's quite significant spread in these, and the spread is also a bit more severe around the Sahara, I have to say. But that's quantified here as well. Within the tool, you're not, well, the idea, what we try to do is we don't try to bombard you with the data. We wanted to make this information and interactivity first in an easy way. But you can access all of the data that's behind the model typically as well. So once the simulation finishes, you can export in open data formats like GeoTIFF or GeoJSON, things like the elevation model, the discharges, the flood depths, the velocities, and some of the other boundary conditions automatically collected by the model. You can inspect aspects about the simulations like the hydrographs and the river network wherever you want to. And the tutorial in a little bit is going to take you through this in a bit more detail. Also things like the flow network and the exposure analysis. I'll leave it there. I've been rambling for a bit again, but then if there's any questions, let me know. And otherwise, we'll take the next half hour for you to explore some of the data behind this tool, and also providing and exporting the data from the platform.